Okay, right on cue. Welcome, everybody, to the May meeting of the Amateur Astronomers Association of Princeton. It's splendid to be together with you tonight, and we have a pretty cool program set up. I'm going to take a little time right at the start, as I usually do, for some announcements, and especially because the skies this month, there's some interesting things. A total lunar eclipse, really fantastic galaxies well positioned overhead, and an amazing collection of planets before dawn. These make up a really spectacular astro palette over the next few weeks as spring now is hitting in full glory. And with our social life returning to normal around the state, we're scheduling some events that I'm going to talk about in a minute, and we hope to get a nice member turnout for some of these. And then after we get through that, I'll turn it over to Victor, and he'll introduce the main speaker for tonight. And we'll hang out together for, let's say, an hour-ish. And when that's finished and any questions are dealt with, we'll move on to a quick intermission and then come back to astronomy by and for members. And in this segment of the meeting, we really like to have members tell us what's going on in their astro lives. So to start that, Rich Sherman is going to do an Unjournal Club. We do need to do a little procedural election of officers. We'll take care of that. And then we'll get into an observatory update and finally open up the mic for any other comments you guys have. So yeah, we got some heavy gravity loaded behind our spring events. Now this coming Saturday, we have an event out at the observatory, and basically this was the brainchild of Dave and I when we were sitting around the observatory one day, and we thought, you know, members would like access to their own equipment and have a chance to set it up and ask questions and maybe show off their hardware. Here's an opportunity to do this, to have a chance to set up your telescope equipment in daylight, maybe learn the ropes if you haven't been setting it up too often, so that you know exactly what you're doing when darkness falls. Now, this idea was to have a get together Saturday late in the afternoon, and only if you felt like it, hang out until dark. But the main idea was to have a meet and greet and get to know each other now that we've shaken off the nastiness of COVID and we're feeling our oats again. Let's get together as a club and see each other in person. So the big idea to do this Saturday is obviously going to be weather dependent. And I did take a peek just before the meeting. It may be a little iffy right now, so stay tuned. We're going to keep it on the agenda, on the schedule here, and we'll send out an announcement either Friday evening or Saturday morning, whether that has to change due to weather. And if it does change, I'll be looking for several of you to suggest what day works best, because we'd like to get this onto the calendar if we have to. We're not going to cancel it, we're going to reschedule it. So right now that's on for Saturday. Now that's a timely event to get out there, because the very next day, there's a remarkable event, one of the full lunar eclipses that's going to be apparent here in New Jersey. Really, the whole eastern 2/3 of the country are going to get a total lunar eclipse. So we're going to be doing that in person, and we welcome members to come out, recognizing that it is a bit late, that the moon enters the umbra around 10:30. Totality doesn't occur for about an hour later. So if that's too late for you, if we can pull this off, and again, weather dependent, we're going to set up our Astro Video Live group, and a few of us will attempt to run our astro cameras through our telescopes and send that into a Zoom meeting. And that notice will go out sometime this weekend. So again, weather dependent. Also, Memorial Day weekend solar observing. Dave reminded me at the Washington Crossing Park Nature Center, just behind where the observatory sits in the park. The exact date and time, again, weather dependent, but this is a tradition on Memorial Day weekend, and Dave and several of you have participated in this in the past, and we are the main show with our solar telescopes and our H-alpha filters. So put that down on your calendar, as well as every Friday night. I think you all know, open house at the observatory, and again, members are always welcome on those Friday nights. It's not only about the public. And then finally, rounding it out on the next meeting, in June 14th, our last regular meeting of the season will be in person at the New Jersey State Planetarium. We will be there in the flesh. Our eyes will be observing photons bouncing off of each other. Can you believe it? So Bill Murray will host that. Bill is an expert in running the system. He's an employee of the planetarium as well as a member of AAAP. So looking forward to that event. The parking situation is fine at the planetarium. You'll park behind it. We'll put this information in Sidereal Times, but just to remind you, there's no reason not to come down to the planetarium on June 14. Well, so obviously some excitement about a lunar eclipse. And what is it that's special about it? It's more about color. So this is the way the full moon looks under a typical month, taken from a small telescope in New Jersey. This is the way it looked last November when we had an annular eclipse. And you guys remember that we zoomed it out with our Astro Video group, and the color change is quite remarkable with this reddish tint, and you can really get great contrast and details. Now, the difference here is we're going to have total eclipse and not just this annular effect. So that bright upper limb will not be there. The whole moon will have turned red. So let's pray to the weather gods and hope we get some breaking up of the clouds Friday late or Sunday late. And if you want to come out to the observatory, some of us will definitely be there. And again, we'll look at the, we'll send a notice, an update on the email. And if you wanted to stay up all night Sunday, you might be treated to this. Has been going on all month long, and the positions are changing, but it's quite amazing to see as many as 5 planets in the twilight before dawn. Saturn, most upper right along the ecliptic, the green line is the ecliptic, and Mars and Neptune on the morning of May 16 are really less than half a degree apart, and there's Jupiter and Venus rounding it out. So this configuration of planets, there is a whole series of near occultations that are occurring, or at least conjunctions, I should say is the proper word. It's a great opportunity to do some planetary astronomy or just look at it with your naked eye. Get up early in the morning and have a look right now. It's not going to last. And finally, as we'd all like to remind ourselves, spring is galaxy season. This has been going on for a month or two now. And this is the way the positions of the galaxies are on May 10th, really tonight at about 10 p.m. You can just see the red line is the meridian, and all these galaxies in red taken out of the Sky 10 planetarium program, showing how close they are to their to the meridian. And it's an amazing thing to sit back with a small telescope and attempt to see. And in fact, I've been working over the past month to try to get some pictures of some of these galaxies that are right down that central line there. Some of the major Messier objects, I've been fortunate to get some decent data on the few nights that we had. Here's Messier 101 taken in my backyard with a 12.5-inch telescope and a CMOS camera. This is one of the more remarkable face-on galaxies. And this, to me, is just to confirm what you can do with small telescope equipment right here in light-polluted New Jersey. This is not from a remote mountaintop somewhere. It's from Titusville. And so a few others just to show you what you can do. The Messier 63, the Sunflower Galaxy. And this guy is a pretty interesting example, what's sometimes called a flocculent spiral, where the arms don't show the same pattern as the so-called grand design spirals like M101. Rather, they're all discontinuous and sort of wrapped up with each other in a lot of star-forming regions in a galaxy like this. Again, very visible right here in New Jersey. As is Messier 95, an example of a barred spiral in Leo. And you can see this right now as well. And a lot of star birth activity as well. And that feature of the bar, which I think still bears some explanation why some spirals form that bar. But nonetheless, very visible from our telescopes here at the park. And then finally, I wanted to share this one with you because I've been wanting to image this for the longest time, ever since back in 2019. Remember the publication of the Event Horizon Telescope where the first black hole was imaged in Messier 87, the giant elliptical galaxy. And that little square in the upper right is what was published as the image of the black hole. But when I took a harder look at the image scale of that data, that black hole, that orange and yellow pattern there really corresponds to about a diameter of about literally about 3 or 4 pixels in the middle of this galaxy. That's the very core, and we can't make it out at all. What we make out is this big spherical thing, and it's one of the hardest things to image because it's just this big spherical halo-like thing, and you can see these rings, concentric rings of different intensity, and that's real. It's just the way the galaxy images, and this thing is one of the largest galaxies in the known universe, or at least the local universe, where we can really study the size of galaxy. And it's thought to have as many as 4 trillion stars and as many as 15,000 globular clusters, whereas the Milky Way has 150 to 200 globular clusters. So this thing is really remarkable. And this is actually the first time I've ever imaged it. And I have to admit, it's not beautiful in the way some of those other spirals are, but it's awe-inspiring to realize what we're dealing with here with M87. So there you go. There's my survey of a few of the galaxies. And if you make your way out to the observatory or set up your own scope, you'll be able to see these even in eyepiece right now. Well, okay, it's time to shut my trap and turn it over to Victor here, and we're going to get on to the main event. So Program Chair Victor Davis, I will stop sharing my screen, and you please do take it away.
All right, well, anyway, so thank you to Bob Vanderbei, who's agreed on very short notice to be our guest speaker tonight. He's going to be discussing his recently published book, Welcome to the Universe in 3D, which he co-authored with J. Richard Gott, Michael Strauss, both also at Princeton, and Neil deGrasse Tyson, director of New York City's Hayden Planetarium. His book depicts in 3D the things we see in the night sky, from planets and moons to nearby stars and out to nebulae, galaxies, and beyond. In this talk, Professor Vanderbei will show some of the stereoscopic pictures from the book and describe the various methods he used to make these stereoscopic pairs of images, which give an accurate 3D rendition of how things really are. A little abridgment of introduction. Bob's a native of Grand Rapids, Michigan. He earned his BS in chemistry and MS in operations, research, and statistics from Rensselaer Polytechnic Institute. He completed his PhD in applied mathematics at Cornell in 1981. He was awarded an NSF postdoctoral research fellowship to pursue his interest in probability theory at NYU's Courant Institute of Mathematical Sciences. Following his fellowship, he moved to the mathematics department at the University of Illinois in Champaign-Urbana. A few years later, he left academia for a job at Bell Labs, where he made fundamental contributions to the field of optimization and holds 3 patents for his enhancements to a new class of algorithms for linear programming. In 1990, Vanderbei returned to academia to teach at Princeton. He is a professor in the Department of Operations Research and Financial Engineering and chaired that department from 2005 to 2012. He also holds courtesy appointments to Princeton's departments of mathematics, astrophysics, computer science, and mechanical and aerospace engineering. Vanderbei holds leadership positions in many professional organizations and is the 2017 winner of the Katchian Prize for his work in optimization. In addition to hundreds of research papers, Vanderbei has written 2 widely adopted textbooks, a popular software package, and 2 popular level books, Sizing Up the Universe, which he talked to the club about a few years ago, is an introductory astronomy book written jointly with J. Richard Gott and published by National Geographic. Welcome to the Universe in 3D was published just this April by Princeton University Press. Bob is a longtime and active member of AAAP. He's an accomplished astrophotographer and regularly posts new astro images on his website, vanderbei.princeton.edu.
All right, so yeah, thank you. And this was the first time I'm giving a talk about my new book, so not sure how it will go. But I don't know if you can all see me in the little windows off to the side with show us, but here's the book. And,
I can see it.
And I could show you how to use it in the little windows, but it might be a challenge. Here's the book, and you open it up, and in the back of the book, it has another little piece that comes out. So now you have, that's the back side of the book, that's the front side of the book. And if you go to look at a random picture somewhere, like, oops, I want to look through the glasses. Over there, you can see, was that Jupiter and Mars? I don't know if you can see it, Jupiter and Mars. And if you hold it up to your face and look through those two lenses, then you see Jupiter and Mars in 3 dimensions. Beautiful. So that's a simple, maybe slightly awkward demonstration. I can have Neil deGrasse Tyson show you a better one in a few minutes here, because he was the one who is the main promoter of the book. He's been on many, many podcasts and shows over the last few weeks, including 3 weeks ago. The book was published 3 weeks ago exactly, and 3 weeks ago exactly at 11:30 at night, Neil deGrasse Tyson was a guest on Stephen Colbert's late night show on CBS. This is some of the artwork that Princeton University Press put together for the book. And if you click on this middle, if I click on this middle link, it will take us to the Princeton University Press website that describes the book. And you can see when you scroll down here that there's another book called Welcome to the Universe. And there's another book called Welcome to the Universe. This is the original one. This is, I think, the problem book that goes with it. I mean, I could tell you a little bit of the story. Those of you who saw Neil on Colbert already heard the whole story. But the 3 other co-authors for many years taught a course at Princeton, an introductory astro course. Neil was one of the teachers of it with Michael Strauss and J. Richard Gott. And it was an extremely popular course, and that's why they were encouraged by, I forget who, the Princeton University Press or maybe the chair of the department, I don't remember which, to actually write a book about the course because it was such a popular course. And so they wrote a book called Welcome to the Universe, which they published, more than 10 years ago. And it's a popular book. And then the 3 of them made another book to go along with it, which had exercises, problems, because the original book was just kind of a book about the universe. It wasn't written like a textbook, even though it was inspired by the course they taught. So then they wrote a problem book to go with it. And then somebody suggested that they should write a shorter version of it. So they wrote 3 books, all of them called Welcome to the Universe with different subtitles. And then I got added into the 4th one because, as Neil deGrasse Tyson says on Colbert, it's awesome to actually see stuff and see it in 3D. And so that sort of inspired them. And by the way, I have been interested in 3-dimensional stuff. I have web pages having nothing to do with this book that I created with 3D pictures that I've made over the years. So if you go to my website, Vanderbei.Princeton.edu, and search around, eventually you'll stumble across some of them. So I've been interested in stereoscopic vision for many, many years. And so has Richard Gott. And so the 2 of us have been collaborating, just sort of just chatting and talking about these things literally for about probably more than 10 years. We share this interest in 3-dimensional astronomy, 3-dimensional stereoscopic stuff. And so that's an introduction to the book from the Princeton University Press. And if we click here, we'll get another Princeton University Press web page, Welcome to the Universe in 3D bonus materials. And there's a link to this on the other page, but I thought I'd just go straight to it. And the interesting thing about this is the main bonus material is that you can listen to Neil deGrasse Tyson read the entire book to you. And so you can hold the book up like this, like I was showing you, and put the glasses up. And if I'm trying to read it, I have to go like this to read it because the text, the caption describing this picture is written down here. And when I'm looking through the glasses, I can't read that. And so, I can look at the picture and then I can read it. And then I can go to the next page and do the same thing and go through all 67 stereoscopic images that way. Or we can just listen to Neil. Want to listen?
On February 6th, 2018,
now we hear him.
Elon Musk launched a Falcon Heavy rocket from Cape Canaveral in Florida with an unusual payload, a Tesla convertible roadster driven by a Starman mannequin wearing a real spacesuit. This stereo image gives you Starman's view of Earth out the front windshield, just as he's about to leave Earth's orbit.
I think that's enough. You get the idea. He reads every caption in the book. I actually went through all of these just a few days ago in preparation for tonight and listened to every one of them and made sure that they matched what was written in the book. And I found a few small things, which I won't mention, but it's pretty awesome to be able to do that. Mm-hmm. And by the way, there's some pictures that we can look at also on the Princeton University Press page, but let me go back to here. Okay, and now if I click up here, it takes me to Colbert. Oh no, sorry, not to there. I screwed up. If I go to the next page, here's a snapshot of what it looked like on Colbert. Let's talk more about stereoscopic imaging and a little bit about how I made some of the pictures in the book. And so, as those of us who are interested in astronomy, in other words, all of us, the notion of what we call parallax is a fundamental concept in astronomy. You view something from two different perspectives, and the things close by look a little bit more shifted in those two perspectives than the things far away. And so we have two eyes. When we look at two things, our brain detects that little bit of shift, and the things that shift more, we don't see two things shifted, it's just one thing, and it looks close. And the things that don't shift very much look like just one thing, but it's far away. So our brains this is really amazing to me that biological things can do this, can take two pictures and make a 3D rendition in a brain out of them. But that's exactly what it is. We all have been doing this all our life, so it's not like new. But anyway, I thought I would show you this. I just took these two pictures just the other day after I was invited to give this talk. This is just standing out in the yard next to my house, just taking a picture of these trees. And I took these two pictures with my cell phone. Here it is. And I took the picture and then I moved the phone over about 3 inches and took another picture. And that's how I got these two pictures. And then I went into Photoshop and just laid them out side by side. And if I were to download this picture, side by side picture onto my cell phone, and then if I were to put my cell phone into the book and then pull up the glasses and look at that picture of those two things through the glasses in the book, that's an actual stereoscopic picture. And that big tree in the front here looks closer to us than the other stuff that's further in the background. And in fact, I can even do that just looking at my screen right now. Not very many people can do this. I can make my eyes look at that left picture with my left eye and the right picture with the right eye. And ooh, now I'm seeing a single thing that's in 3D. And the big tree looks much closer than the other stuff. And it's really beautiful. I love it. And so anyway, maybe none of you can do what I just did. But I do know a few other people in my life that can do that. But anyway, I thought it'd be fun to show you the two pictures individually. So here's the left eye view. Because when we look here, by the way, just looking at these two pictures, they look the same, right? Looks like the two pictures the same. Oh, but if you're really careful here, look here. You see my mouse pointer? Mm-hmm. Yes. So look here, see that little tree there?
Yep.
And go off to the right, nothing. Go over here, see that same tree? Go, oh, look at that, there's another tree here. And we can kind of see just the very edge of that trunk there. And so it is not the same. Things changed a little bit, but just to the casual observer, that just looks like two copies of the same picture. But that's why I wanted to show you the left eye view and the right eye view. There it is. Mm-hmm. They're not the same. And by the way, it was kind of windy out, like it's been windy in New Jersey for the last 3 months, almost every day.
Yeah.
And so the branches in the tree are doing a little bit of random jiggling, just because, in those 5 seconds it took me to move the phone over and take the other picture, the wind blew a little bit differently. But look at the stuff that's not getting affected by the wind. Look at the grassy area. The grass at the very bottom is moving significantly left and right, whereas the grassy part way back in the distance is hardly moving at all. And so that's this whole notion of stereoscopic vision is based on our brains being able to translate that parallax effect, seeing something from two different perspectives, translating it into distance from our view and making a mental image that's three-dimensional. Okay. Oh, so then I took another picture. This is also kind of fun. I held my finger up. So it's exactly the same thing. I held my finger up, I took my phone and I took a picture, and then I moved my phone over and took another picture. I did not move my finger. I just moved the phone from like in front of one eye to in front of the other eye. And here's the two pictures. And look at that. The fingers moved a lot because the finger was just like a foot in front of the camera. And so the parallax of the finger was a large angular displacement, whereas all the other stuff still looks like one thing. But here the finger looks very much different in these two pictures, left and right. And so here it is, same kind of thing, where we can see the two pictures. Now, and here's the interesting thing. When I look at this picture in a stereo perspective, which I can do, and probably none of you can do, when I'm doing it right now, I'm looking at this 3D thing. And the interesting thing is, I don't see one finger sticking up. I see two fingers. And they're kind of translucent because each finger, I also see the stuff behind it. the green trees and the grassy areas, I kind of can see beyond the finger. And that's because my brain, and I think pretty much everybody's brain, when the parallax is so huge, like we're seeing here, the brain doesn't say, oh, that's one thing really, really close. The brain says, oh, I don't know what that is. That's just weird. And so I see it as two things, two fingers that are kind of translucent. But, and here's another interesting thing, because I've talked to many people over the many years that I've been interested in this. A lot of people, when I tell people, hold up your finger, and now hold your finger in front of your face like this, but look at something far away. How many fingers do you see? Don't look at your fingers, look far away. How many fingers do you see up? And a lot of people say, I only see one finger, because a lot of people's brains have this thing where if it's confused, it just shows you one and not the other. and so some people, those are called right dominant and left dominant eyes. And I don't have a dominant eye. My eyes are exactly equal. And so when I look at this picture here in a 3D perspective, the background image looks beautiful in 3D. The trees look perfect. That truck looks far away off on the edge of the road there. But the finger looks like just two weird things sticking in my face here. So yeah, so that's interesting thing how the eye works. And by the way, so this is kind of a representation of how it looks to me. although the background stuff looks in 3D, where in this picture, we're not seeing the background stuff in 3D. But this is how my eyes see my two fingers, because my brain doesn't realize, oh, that's just one thing really close. So anyway, this stuff is all very fun for me and very interesting, but let's go more into the astro direction. So here's one of the pictures from the book, stereoscopic picture of the moon. If you were to get the slides for this presentation or the YouTube video and open it up on your phone, and like I was saying before, stick your phone in the book and then look at this picture through the glasses in your book on the phone there. If you look at it, you'll see that this is a 3D stereoscopic rendition of the moon. Looking at this just as a picture on the screen here, it just looks like two flat things. But if you do the stereoscopic view, the moon looks like a sphere. It looks beautifully like a sphere. And so one of the questions that people ask, in fact, Colbert asked Neil deGrasse Tyson a little bit about this, and Neil deGrasse Tyson did talk a little bit about the moon. How did we make this? Well, it's a complicated story, a little bit complicated, because there's how one could make it, and there's how I did make it. And how I did make it is I used my computer skills to make a really good version of this that's perfect. But there's a much simpler thing that one could do that all of us with a telescope and a camera can do, and that is take a picture of the full moon. Not once, but twice. Not twice the same night, maybe a month apart, or maybe 2 months apart, or maybe 6 months apart, or maybe 3 years apart. Just take 2 pictures of the full moon. They're not going to be the same. And Neil also discussed this a little bit on Colbert. The reason they're not the same is because the moon's orbit around the Earth is not perfectly spherical. The moon's orbit has a bit of eccentricity. It's an ellipse, not a sphere. It's close to being a sphere, but it's not exactly a sphere. And when the moon's at its farther distance, it's traveling slower. And when it's closer to Earth, it's traveling a little bit faster. So how far around, where it is in its position around, is not equally spaced in time. It's not going 90 degrees every 1 week. It's going maybe 89 degrees this week and 91 degrees the next week. But the rotation of the moon is at a constant speed. So if you look at this and you get a full moon at slightly different times of the of its orbit, of its rotational orbit, you get a slightly different perspective on the moon. And you can adjust it to say, oh, this is how it would have looked like through my left eye, and this is how it would look like through my right eye. And that's how I made this picture, which you can see immediately is not perfect, because these aren't perfect full moons. The moon on the left was taken, a little bit before the full moon, maybe about a day before. I'm not exactly sure. I didn't refresh my memory, but they're almost full moons. And I did orient these things so that the rotation really is a left and right kind of displacement. And just for record's sake, these pictures were taken about 4 years apart, these 2 full moons. And if you could look at this through the glasses in the book and see this in a stereoscopic way, as I'm doing right now, because I can let my eyes relax and do that, it looks very 3D. It's really amazing. And this is just because we're getting a slightly different perspective on the full moon, because its orbit isn't exactly circular. All right. One more on the moon. In preparation for tonight's talk, I was looking at this and saying, I made these more than 10 years ago, about 15 years ago. I've taken newer pictures of the moon. Maybe I can make a better version of this. And so I made it better. It's not perfect, but I made another one, and I thought I would show it to you. Here it is. Here's 2 pictures, full moon pictures on 2015 and 2020. So 5 years apart, but much more recent. These are higher quality pictures. If we were to look at them at full pixel size, they're really big pictures. But if you can look at these in a stereoscopic perspective, this looks really beautiful. The moon looks like a ball. It doesn't look like a disk. It looks three-dimensionally round. And it's just like the other one, it's not perfect. And as I'm looking at this right now with my 3D view of this, I can tell you that the southernmost part looks a little bit funky. And I'm not 100% sure why, but I think it's because this is a little bit grayed to the left, whereas this part is a little bit grayed to the right. And that difference in that graying, which I'm not even sure exactly why that happened. Maybe it's how much into the fullness it was. Maybe one's a little bit the beginning of full moon time and the other one's a little bit more toward the end of full moon. But anyway, that slight difference in the brightness makes the bottom part look a little bit off, but it's almost perfect, and it's better than the previous one. So anyway, this is the whole idea, though, is that we can make stereoscopic pictures in different ways. And that's what I want to discuss for the next 20 or 30 minutes, is a few of these different ways that one can do this. And so we don't need to just get our eyes and take a picture or take a camera with two lenses and take a picture and get a stereoscopic view. We can do this other ways. We just need to get two pictures from two different perspectives. And the perspectives on an angular scale should be similar. So if I'm looking at something just on the table here in my room that I'm sitting at, well, I only have to move my eyes back and forth a few inches, and that gives me a sufficiently large angular difference so that I get the 3D effect. But I can't look up at the moon at night, and just because my left eye is 3 inches or 2.5 inches off from my right eye, I don't see the moon in 3D because it's too far away. It's essentially infinitely far away from the perspective of a 3-inch displacement of the two lenses. So to make 3D images of things in the astro world, we have to think of other ways of getting a pair of images that are realistic, but have a displacement. And so that's what this is all about. How can we get pictures that have that displacement to provide us with a stereoscopic view of the thing we're interested in taking pictures of? Oh, before I get into that, here's the moon, those two, see how it's just rotating. You got to get the thing oriented correctly so that the rotation looks like it's purely left and right. As I look at this, I'm not 100% sure I got it purely left and right, but it's pretty close to it. And okay, let's go on. Okay, so this is also just a picture from the book. This is the picture I made of Mars. And similar to what I said with the moon, there's multiple ways one can take a picture of Mars. Mars rotates. One could take a picture of Mars and then come back a couple hours later and take another picture of Mars. And because Mars rotates, and I forget what's the name, anybody remember how long's one day on Mars? I can't remember off the top of my head. Does anybody remember? Nope. Well,
just anyway, a little more than 24 hours. It's about the same as the Earth.
Yeah, it's about the same as here. So if we wanted this to just move, this to look like a rotation of just, let's say, 10 degrees, well, that would be 1/36th of a day. And so that would be like, about 30 minutes, roughly speaking. So take a picture of Mars and then take another picture of Mars about 30 minutes later, and it will have rotated a little bit. And you can use that rotation to make a picture that's stereoscopic and looks 3D. But just to be honest, that's not how this one was done. This one was done similar to the way I did the moon, is I took high quality, the original one that I did with the moon that's in the book, I took high quality, state-of-the-art maps that people have made of these objects from spacecraft and satellites and whatever that have just taken amazing pictures, and then they make a latitude and longitude, just a rectangular picture of this is what the moon looks like, or this is what Mars looks like. Oh, in fact, I have Mars. I have with this on the next slide. There we go. This is called an equirectangular plot of what we have on Mars. So we have an ice cap on the north, we have an ice cap on the south. The Mars's equator is along the center here. And this is, you could think of this as like latitude and longitude, although I don't know if we use that terminology when talking about Mars, but if this was Earth, then this would be longitude, and vertically here would be latitude. And you just make a map that's this rectangular array like this, and it's called an equirectangular projection. So what I did is I took this off of some NASA web page, and then just mapped that onto a sphere, because as I said before, I'm good at this kind of computer programming stuff. I mapped that onto a sphere. So now I've got software that makes a ball out of it. And then I rotated that ball a few degrees left and a few degrees right and made this picture here. So that's just kind of the nerdy way I've done things. But one could just take two pictures of Mars about an hour apart on a really nice night and make a stereo pair that way.
Bob, is
yes.
in the previous picture of the two, that one, yeah. Is that the Martian atmosphere surrounding it?
Yes. That's my understanding anyway. Yes. And yeah, you know what? Now that you say that, I realize I made a mistake in preparing today's presentation. I don't think I made this one from a map, because this doesn't have the atmosphere. I think I did this just from an actual picture of Mars. And then I laid the picture of Mars, just a picture. I laid that picture on the surface of a sphere with my computer programming skills. And then I just rotated it a couple degrees this way and a couple degrees that way. And that's how come we can see the atmospheric part, which we don't see here. So thank you for asking that. That's a really, really good to remind me that that's how I did that. Okay, but there's all kinds of ways of doing these things. So let's keep going. Here's the famous Venus transit. Most of you remember this. Some of you who may be new to the astro world, if you weren't in the astro world in 2012 or earlier, you might not know about Venus transit events. So let me just briefly refresh your memory. There was a Venus transit event in 2004. Oh, and by the way, for those of you who don't know, this is Venus, this dark blob here, this small dark blob, and this is the sun. Venus is passing in front of the sun. So Venus is actually quite close to the Earth relative to its distance from the sun. It's closer to the Earth, but it's passing in front of the sun from our perspective here on Earth. And so there was a Venus transit event in 2004, which I took pictures of using my telescope on the Princeton University campus. And then there was another one of these events in 2012, which is how I took the picture you're seeing here, which I also took with my telescope here on the Princeton campus. And sadly, for those of you who haven't seen a Venus transit, the next Venus transit's in about, I forget, 70 or 80 years in the future. So maybe if there's some 10-year-olds on this Zoom call, you might be around for the next one, but most of us won't. But anyway, here's the cool thing. Venus is transiting. And so there's two different ways we could make a stereoscopic image here. We could just wait because Venus will move. And since Venus is the closer thing from a stereoscopic perspective, it should look like it moved a lot, a significant amount. And then we'll put the sun as the background. So we could just take two pictures, I don't know, half an hour apart or something like that, and get a sense of a stereoscopic. But this is a better picture. This is just a single picture, but the stereoscopic that I'm going to show you right now, I did jointly with somebody who I'm looking at right now on my computer named Aram Friedman, who's part of this group here. I don't know if you all can see him, but I see him waving at me. And he went to a place called Hawaii for the event, the Venus transit event. And comparing notes afterwards, it turned out that he and I took pictures at exactly the same second. And we did multiples of these, but I took the two best ones that were the same. I mean, he had a lot of perfect pictures because the weather in Hawaii is perfect. I had a lot of mediocre pictures and a few good pictures. So what I'm showing you here is one of my good pictures. And in fact, I think it was it this picture that I matched up with the Rams? Well, I don't know. Let's go to the next slide, because the next slide I show you, here are two pictures taken at exactly the same moment from some thousands of miles apart. And it might not be completely obvious to you, but this one here is sticking in a little bit more than this one here. Oh, did I label these correctly? Let me think. I think I labeled these correctly. But anyway, that's because the two eyes, if you like, are not just my eyes 3 inches apart. The two eyes are two different cameras here on Earth, one of them in Hawaii and one of them in New Jersey, taking a picture at exactly the same moment. And from these two pictures, and knowing exactly where Aram was in Hawaii and where I was in New Jersey, I was able to do some trigonometry and figure out the distance, knowing the size of the Earth, figuring out the distance from where Aram was to where I was as a straight line. If you could drill a hole into the Earth to make this straight line distance, I knew the straight line distance. I was able to measure the parallax because I know that the sun is a little bit more than a half a degree in diameter. I think it was 32 arc minutes in diameter. So using that dimension of the sun, I was able to measure the displacement of this Venus here, which, as I say, they look like they're the same, but if I could blink these two images, they're not exactly the same. Just like those trees that I showed you before, just looking at the images side by side, when it's not a huge parallax like my finger was, if it's a small realistic parallax, it just looks like two things that are the same, but they're not the same. And so I measured the difference in this inward bound displacement and measured it to be 21.1 arc seconds. And using that number together with knowing how many miles separated me and Aram here on Earth in New Jersey and Hawaii, I was able to calculate that Venus is 42 million kilometers away. And at this moment, of course, Venus is going around the sun, and so are we. So the distance from the Earth to Venus varies frequently. But if you look up what was the distance between the Earth and Venus on this day, June 5th, 2012, this is the correct answer to like 1 or 2% or something like that. I can't remember exactly how correct it was, but these first two digits are correct. 42 million is correct. 42 point something, the point something might be a little bit different. And so, by the way, so here's the close-up that I was mentioning earlier. This is an overlay of these two images. Here I've rotated them so that the displacement is exactly horizontal. Here's how it looked just from the two images as they were from our two pictures that we took. So you have to do some, you always have to do a little bit of tinkering, rotating pictures to get the translation to be horizontal. Anyway, so there you can see that they weren't exactly in the same place. That's how much. And by the way, Venus is about the same size as Earth. So you'd expect somebody who's in Hawaii and somebody who's in New Jersey takes a picture of Venus, the displacement should be about half of the size of Venus, which is about what we're seeing there. And so all these things are very consistent when you think about them. They make sense. Okay, let's move on. Oh, before we move on, this is just one more picture from that same event where, and if you look at this one through the glasses, it's again in stereoscopic. Venus looks like it's in front of the sun there. And this was just done by literally taking pictures like 10 minutes, or I forget exactly how many minutes apart, because Venus is moving, and then rotating it correctly so that that motion of Venus relative to the sun looks horizontal. And so this is literally just two pictures of the same transit taken from the same place because Venus is moving. And okay, let's go on. All right, so let's move out a little bit further. And now I'll just describe over the next 10 minutes or so some of the pictures further out and how I made a 3D picture out of it. So Comet Lovejoy is a comet. And if you look at this in stereoscopic view, the comet looks like it's well in front of all the stars. And the stars in this stereoscopic view all look like they're sort of equally far away, because relative to the comet, they're basically essentially infinitely far away. So I didn't need to make a 3D perspective of the stars here when I'm only trying to make a 3D view of the comet. And so what I did is I wrote some software myself to extract the stars. And this has become popular in the astrophotography world, Star Exterminator and blah, blah, blah. Those things didn't exist when I did this. So I wrote my own code to detect where the stars are, and then make two things. One picture that's just the stars without the comet, and another picture that's just the comet without the stars. And so once I had the comet separate, I could do the kind of displacement to make it look 3D. So to be honest with you, I didn't get in a spaceship and take two pictures of the comet from two very different perspectives. This is just computer skills. But some things are more accurate perspective, and I'll show you some in a minute. This is not one of them, unfortunately. So this is one of the pictures from the book. So if we click on it, it takes us to the book. So there it is in the book. Oh, and we can hear Neil describe it if you want.
Jupiter, 11 times Earth's diameter. Jupiter is a gas giant composed.
Okay, maybe that's enough. So this is on the Princeton University Press webpage. But this is just a single picture of Jupiter, its moon Ganymede, and Ganymede was casting its shadow onto Jupiter, which I was really excited about this because it was right on top of the great red spot on Jupiter. And so this 3D picture is just made from a single picture of Jupiter, where I just applied my math skills like I said I did for Mars, where I just took this thing and said, okay, this is not a disk, put this onto a hemisphere of a ball, and now rotate that ball just a few degrees this way and a few degrees that way. And that gives you a stereoscopic perspective. Because we couldn't wait, 10 minutes and then redo a picture to get the stereoscopic here, because then the black spot has moved. And then it would look like the black spot is in front of Jupiter, but actually the black spot's on the surface of Jupiter. So as much as it would be fun to have just taken two pictures 10, 15 minutes apart and get the stereoscopic view of it from that, that wasn't possible with, I hope my things are still working. That wasn't possible because of the shadow of the moon. Okay, so that's one. And then I thought it'd be fun to show you that I also made, just a few months ago, I did a very careful computer program to make 3D versions of the moon, of Jupiter and its 4 major moons. And if I click on this, it takes us to the web page that I made. And here it is. And let me make it smaller. And maybe slide it down a little bit. And so you can click this button to set to now, and it sets the clock to the current time. And my code knows where the moons are as a function of time, and it puts them in the correct place. And we can also rotate things a little bit. And so it doesn't have to be completely on the equatorial plane of Jupiter. And so when the moons come in front, they also cast their shadows, which I was very careful to do. Oh, and I can make it a little bit closer. How do I do that? Let's zoom in. There we go. Now we're going to have to wait a little while for the next transit to happen. Shall we wait a few more seconds? Okay, there's one going around the back. Okay, and how long do we have to wait before it comes across the front? Pretty soon here. I hope. Shall I zoom out and see where things are? Oh, here it is. Oh, there we go. Oh, here comes another one. And here comes the shadow. There's the shadow. So the sun isn't straight behind us. It's behind us, but off to the right. So I had a lot of fun making this. And for those of you who want to play with it, there's the link up here. Okay, let's go back to the slides. All right. Okay, so that's that. All right, so let's get back to talking about parallax. And for those of us who have been interested in astronomy for a long time, we all know very well what parallax is. And I described it a little bit by holding up my finger, but here's the kind of the standard picture that often you would see in an astro book. Because astroparallax, the displacement is the Earth going around the sun. So if you take a picture of something 6 months apart, 6 months before it transits at midnight and 6 months after it transits at midnight, so when it's transiting right at sunrise and right at sunset, take a picture of a star, you're getting an angular change, which is shown by this little red dash line here, because we're seeing it in a different perspective. And so relative to stars which are 1,000 times further away, the so-called background stars, those don't look like they're shifting because those shifts are so tiny, you won't really notice them. Of course, technically speaking, everything's shifting because we're the ones moving. But things that are thousands of times further away, you don't detect that motion. And so we can measure the angular change in the position of nearby things. And this angular change measured in arc seconds. There's 360 degrees in a circle, 60 arc minutes in a degree, 60 arc seconds in 1 arc minute. So if we measure this angular change as an angle measured in arc seconds, that's the parallax. And the distance to nearby star, well, everything can be measured in something called parsecs. And parsecs is the reciprocal of the parallax, because a big parallax means something's close, not something's far. We want a big number for things that are far. So you take the reciprocal of the parallax, and that's the distance in parsecs. And so, as probably maybe everybody on this Zoom call already knows all this, I thought I would mention it briefly because you can do this to get stereoscopic pictures of stars that show the nearby things differently. So here's 2 pictures that I took of Barnard's star. And again, these 2 things look exactly the same, but if I were to blink the 2, you would see that all of the stars look exactly the same, except for this bright one here is shifting a little bit left and right as I look at these 2 images. Oh, in fact, I can actually convince you that that's true. Look at this little star right here. I hope you can all see my mouse and its angle from the bright star, from Barnard's star. That's up and to the left, almost at a 45-degree angle. Look at the same star here. It's still, that dim star is still up and to the left, but it's not a 45-degree angle. And it's not the dim star that moved, it's the bright star that's displaced a little bit. So if you could look at this, and this, by the way, is a picture from the book. If you could look at, if you buy the book and look at this with the stereoscopic lenses, Barnard's star will look like it's closer to you than all the other stars in this picture, because Barnard's star is a lot closer than all of the other stars in this picture. And by the way, just so you know, I've told you about a whole bunch of things already. I should mention, and all those things I told you about, I mentioned a little bit about how I quote unquote cheated to do things. And just so you know, I also cheated here a little bit, because this motion that I'm getting the 3D perspective out of is not the parallax motion. I've taken 6 pictures of Barnard's star over the years. Here they are: 1, 2, 3, 4, 5, 6, 5, 4, 3, 2, 1, 2, 3, 4, 5, 6, 5, 4, 3, 2, 1. Barnard's star over time is moving south. That is not its parallax. That is because Barnard's star is relatively close to us. Its so-called proper motion is sufficiently large that over the course of years, it has moved in a real sense. It's moving. We're going around the sun, so there is some parallax, but that's not the main thing we're seeing here. Parallax would be left and right in this picture. And by the way, I don't know if you noticed it, but as I do these 6 things, there is a little bit of a left and right, back and forth. 1, 2, 3, 4, 5, 6. You see that little bit of a left and right? That little bit of left and right jiggle is the parallax. The vertical motion is just the simple fact that Barnard's star, because it's not far from us and it's got a fast velocity in the real life, it's making a significant motion over time. And so, in fact, here's an overlay of all 6 images with the times at which I took them. And as you look at this, you can see it's going consistently south, but there is a little bit of a wobble. You can sort of see this wobble left and right. And so I did take these pictures and measure the left and right wobble, and was able to accurately measure the distance to Barnard's star using these pictures that I took with the telescope on my driveway. But to make that 3D picture that I was just showing you, it's just, I think, this one and this one. June 21st and June 6th, 1 year apart, are the 2 pictures I think that were used to make this picture here. So here the translation is left and right because these pictures are rotated 90 degrees from the actual pictures. North is to the right and south is to the left. Usually when we take pictures, we put north up and south down. And if you're not even sure that that's really correct, look at this little double star here and this kind of brightish star over here. And now let's go over to Barnard's star. There's the double star, there's Barnard's star, there's the brightish. So if I take this picture here and rotate it clockwise 90 degrees, I get one of these 2 pictures. I'm not sure which one. So again, a little bit of cheating to make an interesting picture for the book, but there you go. So now let's talk about some of the other pictures in the book. The book has various star charts. It has winter, spring, summer, fall. I guess we call it autumn. And it also has north and south. To make these pictures, I used data from Gaia, the Gaia Space Telescope, which has been taking incredibly accurate imaging data of stars, has measured the parallax, the brightness, the color, the position, right ascension and declination, all the information one would need to make a beautiful 3D diagram. And so again, just looking at this, it just looks like 2 pictures, but if you can go look at this in stereoscopic view, as I'm doing right now, Sirius is standing way out in front of everything else. And Procyon is standing out a lot, but not as far as Sirius. And Pollux is the next closest, and Castor and Aldebaran are also standing out nicely. And most of the other stars are not equally distant, but they're further into the background. And so I made these pictures by first getting a picture of the Milky Way and removed the stars. I didn't have Star Exterminator. I wrote my own code to remove stars, but I got rid of the stars from the Milky Way and then rebuilt the stars with code. And so I used actually data that I got from one of my favorite stars. Its name is Vega. I took really good pictures of Vega some years ago, just a single star. And I used that picture of that one star to make all of these thousands of stars in this picture here. And I just changed the color, changed the brightness, put the position, did the parallax, and made this stereo view of what the winter sky looks like from our, actually this is from the equator view, not from New Jersey view. This is a winter star chart as viewed from the equator. Okay, so, and then for fun, I also did something called our solar neighborhood, where I did the same thing using Gaia data, but instead of showing how it looks from our perspective, I went, I think, 15 light years away, or maybe it was 15 parsecs, I don't remember which, and made a picture of what does the sun and the stars around it look like viewed from this several light years away, and made this picture, which also looks really awesome if you can view it in 3D. And it's also in the book. And okay, here's a picture of the Crab Nebula. I did not make this picture. This picture was made by people who work for NASA. They did it with data. In fact, if I click on this, we take us to the web page, a PDF file. Here's from the Astronomical Journal, which is the most prestigious journal in the astro world, a hyperspectral view of the Crab Nebula. Here's an explanation of how they figured out the depth of all the different pieces in the Crab Nebula. We don't have time to read this, but just so you know, it's these people who figured out this 3D perspective. And I looked to see where I found that image, and I couldn't re-find it just the other day, but this is like 12-year-old paper, and I didn't spend that much time looking for it, but it's probably still out there on the internet somewhere. But I don't think I made it. Maybe I did. Maybe I don't remember. It's 12 years ago. But it's from the data that they got telling where the stuff is in this image. Okay, we're getting close to the end. Here's the Andromeda Galaxy. I did this one. Again, if you take a picture of the Andromeda Galaxy, you see lots of stars. Those stars that you see in the picture are not part of the Andromeda Galaxy. They're part of our Milky Way galaxy. So first thing I did to make this is I removed all the stars because they're local to us. And then now I just have actually 3 galaxies, boom, boom, and boom. And then I just kind of did a little bit of photoshopping to rotate things because it's kind of obvious that this should be a disk that's sort of tilted a little bit. And so I just kind of made it by tinkering with things. And here is the last one, the Hubble Ultra Deep Field. I wrote the code to make this 3D image. And by the way, many people who I've talked to who've already gotten the book and have already looked at the pictures in 3D, many of those people have said this is their favorite one. Because as you look at this just in 2D, as probably everybody's seeing it right now, it's interesting because all these things are galaxies, and it's amazing how the colors are different and the sizes and the shapes and blah, 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 but it looks just like a flat thing. I made a 3D thing, and I did it by guesstimating how far away these galaxies are by basically how big they are. And so I wrote code to find all the blobs in the picture, and for each blob, how big is this blob? And if it was a big blob, I assumed it's kind of close. And if it's a small blob, I assumed it's far. And I made a 3D picture that way. And it really looks really cool when you see this in 3D as I'm doing it right now. Oh, it's so cool. It's really interesting, actually. And so it might not be perfect. Some of these galaxies might be further than I'm depicting them or closer than I'm depicting them, but still, it gives a nice representation of how the 3D universe looks. And that's it, other than just a picture of the carpet in Peyton Hall. And if you could, and this is also in the book. And if you can view this in stereoscopic, you're looking down the hall. And you're seeing all the way down, and it looks pretty. Those of you who've been in Peyton Hall have probably seen this, and probably that's most of you. It's fun to be able to actually get in a book something with look through these glasses, and it looks just like it did when you were in Peyton Hall. So that's it. That's all I had to say. I'll stop my screen share.
Wow, that's terrific. I have a quick question, Bob. When I use the sort of cross-eyed view to see things in 3D, I'm seeing it backwards. The globes are concave, and I'm seeing things in the background that are in the foreground. What's with that? What is that?
Because you're doing it cross-eyed. You got to do it splay-eyed. Your left eye has to look at the left image, and your right eye has to look at the right image. Cross-eyed means your left eye is looking at the right image, and your right eye is looking at the left image. And so when I've made 3D stuff, and as I said already, there's a zillion 3D things on my webpage. Half of these web pages are cross-eyed 3D pictures. Half of them are splay-eyed 3D pictures. So the pictures that are in the book are all splay-eyed because the lens, when I'm looking through the lens on the left, is pointing my eye to look at the picture on the left, not on the right. Does that answer the question?
Yes.
Okay.
Yeah, that's it. So I have a feeling this is going to be a frequently viewed meeting. So people can have another chance to look at those great 3D images. It's terrific. Thank you very much.
Thank you.
Any other question?
Yeah, I have a question for Bob. This is a show. Bob, excellent presentation. Loved it. I also tried the cross-eyed method, I guess, that Victor talked about. And I didn't see it the opposite. I was seeing it just like an overlay. Things were popping out in 3D. So am I maybe imagining I'm doing cross-eyed and am I not? I'm not, or what could be?
So you're looking at the pairs of images on the screen.
Yeah.
As we're talking, right? Is that what you're talking about?
Yeah. As you were presenting it, and I was trying to bring them together. Yeah.
If you're bringing them together and you're seeing the sphere pop out as a sphere, not as a cup, then you're actually doing it splay-eyed.
I see. Okay.
Yeah.
All right.
I mean, it is interesting because these are two different things, but they kind of seem similar in a way, So,
right. Okay. Thank you.
Yeah.
I've got a question as well. Practically speaking, how far can you use this parallax method in terms of actual distance of a star? Like practically, how far out can you go with it?
Oh, that's a really good question. The Gaia data has parallax information even for stars in M13, the globular cluster, which is tens of thousands of light years away. I don't remember the exact number. Was it 30,000 light years? I forget how far away M13 is. So I used to know the answer. I'm only speaking from memory at the moment because I did this Gaia stuff a few years ago. But I think the Gaia data goes out thousands of light years, which is really amazing.
But for us here on Earth, though, using the amateur instruments that we use, practically speaking, how far out can you practically use it for?
Oh, I see. Maybe 20 light years might be about the limit.
Okay.
Because 1 arc second is 1 parsec, and 1 parsec is 3 point something light years. And 1 arc second displacement is pretty small because the resolution of most cameras and telescopes is about an arc second. But if we're taking a centroid, you can actually centroid a star with better accuracy than just knowing the diameter of the star. And that was one of the things that I found kind of interesting when I was first learning about some of this, is that you could figure out where a star's right ascension and declination is with a precision that's smaller than an arc second, like maybe 1/10 of an arc second, or maybe even, if you're really good, maybe 100th of an arc second, just because we know that that star is a blob. You know, it's kind of like, it's a Gaussian, it's a bell curve. And so even though it's a blob of intensity that's spaced out over about an arc second, if you figure out where the middle of that blob is, the average of that blob, a weighted average of these things, you can figure out that weighted average to a fraction of an arc second. Even though that's smaller than 1 pixel, you can do that accurately to a fraction of a pixel. In fact, people who have in the past actually defocused the telescope a little bit to make this blob a little bit bigger, because then you get a better, the pixelization becomes less of a factor when you're figuring out the average of these numbers. And you get actually a better measure of where the center of that star is if the point spread function, the blurriness of that star, is a little bit bigger. So even though most amateur-sized telescopes, the resolution's about an arc second, if you're totally into it and take pictures with your camera and accurately do some data analysis, you can figure out these displacements to 1/10 of an arc second. Or maybe if you're really, really good, even better than that, but maybe I won't go that way. So if it's 1/10 of an arc second, that's 10 parsecs, that's 30 light years or something like that.
Got it.
So, yeah.
Thank you.
Yep.
Robert, it's Aram.
Hi, Aram.
What about Wolf 359? Do you recall what the distance there was?
I don't remember. Do you?
No, but that was a 3D image as well that you did.
Yeah, so that was just tinkering with things. Shall I refresh my memory and read it?
Was that in the book?
I don't remember. Is it in the book? No, just the Quasar 2373 is in the book.
I'm talking about the one with New Horizons, where you took they took the probe and you took one at the same time.
Yeah, that's right. I don't remember.
Okay, well, I recall you'd sent me a 3D image of that, and it was pretty awesome.
Yeah, I'd forgotten about that. Yeah, you're right. I don't remember the numbers though. Sorry.
All right. Really fun, by the way, tonight. It's great to see.
Thank you.
Bob, could you describe a little bit more about the lenses and what allows the viewer to see 3D using the lenses in your book, or perhaps in a stereo viewer, compared to most of us have a dog of a time trying to make our eyes do that in a relaxed state?
So yeah, I can do that. So the whole purpose of these lenses is just so that you can hold the thing you're looking at really close to you. It's only about 6 inches apart. If you can hold something up 6 inches away and focus on it, which I can't, then you could do it without the lens. And when things are really close, in fact, this is how people tell people to get a splay-eyed stereoscopic view without lenses. Here's what they say. Hold the thing right up like this. And then, can you guys see me? Yeah. Hold it right up like this and then go out. Because when you hold it like this, even though it's complete blur, the left eye is seeing the left image, the right eye is seeing the right image. And as you just move out slowly, you still just see them as two things overlaid as one thing. And then when it comes into focus, it's 3D, and it's splay-eyed 3D because your brain didn't point your eyes at things differently. So the whole purpose of the lenses is just to make this something trivial that everybody can do. And the other thing, by the way, is also to block a little bit of the other picture, and that's why for some people, it's better when they hold it a few inches away from their face, because then through the little hole in that's this lens, you only can see the picture. You can't see the other picture because it's blocked by the cover here. But if I put up close enough, now my eye is sufficiently close that I have enough angular view that I can actually see both of those things. And so that's why for some people, it works better to hold it a little bit further away, because then your eye cannot see. The left eye can only see the left image. The right eye can only see the right image. And therefore your brain knows what to do.
Hey, Bob, you alluded to something earlier about dominant eye. And I think before the meeting started, I think I mentioned that I don't know if I can do stereo, because when I bring my hand up and then bring my finger in, it doesn't go to my nose. It goes to my one side, my right eye. Can you speak to that?
I don't know how much I can speak to that, actually. Okay. I can tell you a story.
Sure.
When I was in grad school many, many decades ago, I had a friend who was quite athletic person. I think we used to play tennis together a little bit. And he and I had the same thesis advisor. We were friends. And at one point, he told me something which surprised me. He said he only sees out of one eye all of his life. One of his eyes didn't work. I'm like, wow. And you can play tennis? So our brain is like, it's more than just this stereo view. You know, I can close my one eye and I can look at things on the wall over there. They seem further away than things on the table right in front of me, because my brain understands this 3D world we're living in. Right. And so there's multiple levels of what 3D is. And I definitely like the stereoscopic. When I take my hand off my eye, I see it in more 3D, but I still, with one eye blocked, I can still understand that it's 3D.
Yeah.
So,
well, in my case, and I think when I was young, they tried to use a patch on my dominant eye to try and strengthen my weaker eye. Now, my weaker eye has a little bit of a movement, which makes it difficult for the brain to do stereo. And I think that's really what it is there's a tiny bit, and there's a technical word for it. Where's Raphael Caruso when you need him?
Dave, do you have an astigmatism?
I also have an astigmatism. Yeah.
Yeah.
So, so I would love to buy the book. I'll buy the book just to support you, but I don't know if I'll be able to see the exact everything that you're seeing.
I'll be very curious to know how it works for you.
I will. I'll let you know.
Yeah.
And Bob, is there a reprint going on? What's the current status on being able to get the book?
So, yeah, Amazon was sold out because it went to #1. But that didn't mean the publisher didn't have more. It just meant the publisher hadn't sent them from their warehouse to Amazon. And so I forget the numbers. I think it was something like 5,000 was how much they had sent to Amazon. And those 5,000 were sold in the first 2 days or something like that. But the original print run was 25,000. So, and not all of it goes to Amazon. There's Barnes and Noble, whatever. There's other countries that buy it, India and China and blah, blah, blah. So not all 25,000 are eventually going to go to Amazon, but something like a half or 2/3 of them do go to Amazon. So the fact that there were only like 5,000 or 7,000 when they sold out, they just had to get more from the warehouse. And
I just went on to Amazon, and they seem to have books right now. I got to place an order. I didn't get a chance to do that.
Yes. Yes. I was going to guess
that's not a plug, necessarily a shameless plug for you, Bob, but you can take it that way.
Thank you.
We're at the part of the meeting where we will call upon one of our members who has volunteered to give the famous Unjournal Club, and that would be Rich Sherman. And I see you there, Rich. Are you in Florida or New Jersey?
I'm in Florida. We'll be in New Jersey tomorrow, though.
Oh, what a guy. Okay, well, it's great to have you coming in from Florida there. And so I'm going to let you take her away. So about 10 minutes or so, and we're going to have Rich introduce his topic and take it away, Rich.
All right, I'm going to share my screen. Hopefully this will work. Can you see my screen?
Yes. Yes.
All right, super. And I'm going to try to hit Shift F or F5 so we can see it full screen.
Looks
all right, great. Well, hello, everybody. Thanks, Rex. I thought I'd just talk a little bit about the International Dark Sky Association. I've been a member of the association for a couple of years now, and I had an opportunity to reach out to them this week. I had a very positive interaction as I had some ideas about some resources I wanted to acquire. And I found out I didn't really know quite as much about the International Dark Sky Association as I thought. So I thought maybe I'd share some information about them. And as a member, just like as a AAAP member, pretty passionate about dark skies, as I think we all are. So as a member, your membership's inexpensive. It starts at $35 per year, $15 if you're a student. But yeah, just a mere $35 a year. The organization's been operating as a 501c3, a not-for-profit, since 1988. If you join the International Dark Sky Association, you get a welcome package and get some forms and a nice little neat magnet. Now I need to stop here for a second and ask, are we still taping this, or are we not videotaping, whatever the term is, this section of the...
We're still recording and it's still live to YouTube, correct?
Okay. Great. All right. Thank you, Dave. So one of the cool things, maybe the last session or two sessions ago, I talked about trying to get some printed copies of the brochures. They have some very nice brochures, 4 or 5 brochures, and you can see the names listed here. Protect the Night, light pollution, AB, can harm wildlife, crime and safety, light pollution, waste money and energy, etc. And as a member, for a mere $35, they will send you, upon request, 100 copies of any or all of the brochures. So I have in the mail coming to me about 500 brochures, plus another 100 postcards. Why I reached out to them today is because I was confronted by my little local HOA here that they put in all new mailboxes with bright non-directional lights that splay out onto the streets. And, having done a little bit of reading about the International Dark Sky Association, I got some help from Rex and Sarabi when I presented to the city council here down in Florida. Safety is a real issue when it comes to lighting, not just the passion that we have for astrophotography and the night sky. Obviously, wildlife's important to me. I love wildlife. Also health. I like my health. There's also some good evidence that sleep disruption and higher instances of certain diseases occur when we have excessive lighting. But the big thing that I struggle with is I had let's just say a discussion, and that'd be a nice way of putting it, with the head of the HOA who came over to address the fact that I had put a switch in and turned off the light at the mailbox. And he was telling me that was unacceptable and unsafe, when the reality is his ignorance was was very obvious to me when, especially with folks here in this area of Florida, some folks are of a certain age where it's very difficult to see into the shadows when you have bright lights periodically that appear along the street. And the president of the HOA assured me that I was in fact wrong about that. So I decided to go and contact the International Dark Sky Association to get some brochures. It was not the interaction that I was hoping. I was hoping to get some information and then present to the HOA maybe in the fall timeframe, but things got accelerated. But the cool thing about the HOA is you got a not-for-profit, $35 a year. We can get 500, each of us could get, whoever joins could get 500 brochures, 100 postcards. And I thought that might be interesting for us as we have our outreach programs, as we have our visitors that come to the observatory, that we could actually help spread the good news about safety, health, crime, and the joy of the night skies, with free brochures that come for a mere $35 per year. they come in various languages as well. Now, time for a secret. One of the cool things that I got in my welcome package a couple of years ago was a little magnet that I stuck on my car. I love dark skies. So I liked it, just get the word out, get people thinking about it. Of course, in the car wash, it washed off. I called them and they said, yeah, we'll send you some. How many do you want? So the secret is if you join and you want to stick them on the car of the head of the HOA or of the, you said this was not being taped, right, Dave?
Oh, it is.
No, I'm just joking. Or if you wanted to put them out in your community or share them with friends and family, they'll send you a bunch of them. And they were really very accommodating to that. So that's my little secret about that.
Just let me know if you're going to say anything bad and I'll put you on mute.
I'll try to hold my profanities back. So lots of information, lots of really valuable information there. As I mentioned, helped overcome logical but incorrect theories. Most people in the world are trying to do the right thing. And, I think as amateur astronomers, we can help to educate folks about, the night sky, about beautiful things that we can see, but also about lighting as well. And the International Dark Sky Association also helps. There are chapters that you can find online. There's a link here. I know it's probably a little bit hard to read, but I'll tell you why in a moment. They have materials for educators. If you're in schools or if we go to schools, we can download some information. They have a great film that's also downloadable and can be shared if you want to share it at a meeting, Losing the Dark. And they have other videos, including a TED Talk that you can find on their website. They have a whole section on lighting that you can share with homeowners associations or neighbors or just to educate yourself, which includes some helpful guides to lighting. In my conversation with them, they were excited that they have a new website coming soon. So they've been growing rather quickly, which I'll mention in a moment. So they've invested some money into a new website, but for now, the current website works very well. I'm looking over here because I have two screens, so I'm sorry if I'm looking back and forth here. You can sign up for the newsletter, which I get. They have a YouTube channel. They, of course, on all the major social media platforms. What I didn't know is that they had a virtual conference. And they had one last November, in November. Yeah. And I talked to them this week and they'll have a virtual conference again this year. They'll have registration that opens in late September or early October. It's free and you can listen in and we can listen in and learn or participate, whatever we'd like to do. And they also have a photography competition with, obviously, our club has some fantastic, we just heard Bob and looked at some unbelievable images. Of course, some of those were images that he adjusted, but we know that Bob and Rex and others are fantastic astrophotographers, but they have each June to July, I think it's around the first day of summer into July, they have open submissions for their photography competition that's coming up in a couple of months. As a merchandise coordinator for the AAAP, they have merchandise as well, that you can wear or to help get the word out about the importance of night. They have various logos that you can purchase, different logos. I think they have 4 or 5 different logos. This is just one of them. So I use those really hard to read text because I kind of feel like, it's a analogy of how we feel when we have dark polluted skies. Everything just kind of there's too much light out there and we're losing the clarity and the contrast that we love as photographers and astronomers. So the association is growing very rapidly. As mentioned, they're putting up a new website. It's growing about 15% per year. They didn't share the exact number of members, but you can actually go online and find advocates if you had questions or wanted to figure out how they were able to, in their local chapter, to get an International Dark Sky designation, or if they had challenges with city council or homeowners associations, you can go online and find advocates. Several years ago, I had a friend who had a young son who succumbed to a terminal disease, and I went to his wake, just not to get down on stuff, but it's amazing how wisdom comes out of the strangest places. And in the eulogy, his kindergarten teacher had said that all the other kids were amazed at how he never complained, even though he had a neurological disorder and everything just took him forever to do. And they asked him, well, you know, his kid buddies asked him, how come you don't ever complain? He says, complaining just makes things take longer. And so I've always thought about that. I mean, it's been 15 years since that moment, but, you know, I feel kind of like, you know, that's a great point. Let's not complain about the night skies and the light pollutions and the Elon Musk. Let's try to do something about it. You know, Rex and Sarabi have done work in their townships. In fact, Rex and Sarabi, I shared the ordinance that was written for Hopewell Township with our local township here in City Council, and continue to follow up with them as well. We can become advocates, or you can become an advocate if you wanted to. You just watch a video and fill out a form, send an email, and you become an advocate to help others as well. If you want to get that involved. But clearly, people here are very busy, right? And not everyone has the time. But from my perspective, for $35 a year, you can empower others to keep up the fight and keep pressing along on what many of us believe, I think, is an important thing as amateur astronomers. It takes maybe 3 minutes to fill out the form and put your address in and pay your $35. And as I mentioned earlier, you know, we could donate or share extra brochures. I'm going to have lots of brochures. I won't have it by the time I come up this week. But I'll drop off a lot of brochures if Rex and the board would like to receive them. I'm happy to share those with you all. So why not try to have 100% of AAA members be part of the International Dark Sky Association? I mean, I know 100% goal is often difficult, but we're amateur astronomers at $35, and the amount of resources that are available to you, it just seems like something that's really doable. It's long been said that the key to happiness is being part of something bigger than yourself, and I think that's probably especially true as amateur astronomers. Understanding the cosmos and where we are kind of fulfills us in our amateur pursuits and our hobby. It really makes us happy and joyful when we study the cosmos and understand where we are. So I had all those messy links with those white out because of light pollution on my screen. Here are those links that I had previously had that were probably too hard to read about the photography contest, the conference, how to find an advocate, and how to become an advocate as well. That's all I wanted to talk about. The folks are very accessible. There's a phone number right on the. I don't want to bombard everyone with information because we have a very short period of time, but there's a phone number there. They answer the phone, believe it or not. When I got in voicemail, I got a call back in less than a half hour. I found them to be very collaborative and very enthusiastic. And hey, there's lots of resources there, and dark skies are important to us all.